Yes, so recently I began studying about machine learning and deep learning and also convolutional neural networks. And then in the beginning, I had a challenge visualizing the concept of convolutional neural networks. So in my search online, I found up an explainer. So this is like a tool that is on the browser that actually explains various layers in a convolutional neural network as applied in image classification. So I want to take this time show you and explain briefly how the CNN works, and I hope you get a better understanding. And this tool is online, so I'll also leave with you the link so that you can also check it out, play with it because it's actually interactive. So you can also learn how CNN works. Okay. So what is a convolutional neural network? So in machine learning, a classifier assigns a class label to a data point. And then, for example, an image classifier produces a class label, e.g., for example, a bird, a lifeboat, ladybug, pizza, a school bus. So it assigns a label to an input image. And a convolutional neural network, or CNN for short, is a type of classifier. So it excels actually in solving these kinds of tasks such as image classification. And so a CNN is a neural network, an algorithm used to recognize patterns in data. So neural networks in general are composed of a collection of neurons that are organized in layers, each with their own learnable weights. So we will talk about this, and biases. So let's break down a CNN into basic building blocks. So here you can see various layers. So a tensor, let's talk about a tensor. A tensor can be thought of an n-dimensional matrix. So it could be 3 by 3, 1 by 2, 2 by 2. So in CNN, like this one, the tensor is three-dimensional. Here we have a red channel, a green channel, and a blue channel, of which each channel has 2 dimensions. So we have 3 dimensions. And the output layer, of course, we have only one. It's a one-dimensional output because we have only either a lifeboat, a ladybug, and just one dimensions in the output. And then a neuron can be thought of as a function that takes a multiple inputs and yields a single output. So if, for example, this is a neuron here, it takes multiple inputs and gives you one output. So we will learn this. And then a layer is simply a collection of neurons. So these are a collection of neurons. And then of course they may it performs a same operation. In this case, it's a convolutional layer, and then the other layers like the pooling layers, the activation layers, and others. So they also kernel weights, and biases. So these are unique for each neuron. So when we have a neuron, it has a kernel here, so it's which actually tuned during training. So they are tuned or fixed during training. So in this case, we're not going to talk about training, how they come about. In summary, they are like the feature extractors. So they extract features from the image. So they can just detect the edges of the image. They could detect various features of an image. So kernels and the weights are simply feature extractors. And then at the end of it, a CNN actually conveys a differentiable score function. So at the end of it, we want to identify or classify an image to a certain class. So this is what happens at the end of the convolution CNN model. Okay, what does each layer of the network do? So this will be our discussion. So in this case, we have a convolutional neural networks. The first layer in this, we have 3 channels of an image. So in this case, we are trying to classify this number of classes. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes. So we have 10 images. We want to classify them accordingly. So we have a car, we have a cup, we have a sport car, we have a school bus. So these are images, and an image, a colored image, has 3 channels: the red, green, and blue. So we take these 3 channels, separate them. We have the red channel, the green, and the blue, and then feed them to a convolutional neural layer. So the convolutional layer are actually the foundation of CNNs. So they contain land kernels, or these are feature extraction maps, which extract features that distinguish different images from another. So we want to distinguish features of various images. And then the convolutional neuron performs an element-wise dot product. So in this case, you have the image, and then what happens here is the dot product. So you take an image, an input image, in this case is the black, then it has a dot product between, this is the kernel map, or the kernel weights, and then you have it as a 3x3 matrix. Then you slide over the image. So the image is 64 pixel by 64 pixels. That's the length and width and height. And then after all these calculations, we are able to extract certain features of this image. So this is actually the convolution. Then from this we obtain a feature which is actually fed into another layer of the convolution. So the elements, of course, after the 3 channels we extract features from the 3 channels, we sum them and then add a bias to this, and then we have an output. Okay, so after this, it happens for all the feature maps. So this is actually for one feature map. It's operated upon every channel, and then we come for another feature map. The same thing happens. You add and sum them, you obtain all these features. So this convolutional layer has all these features, and then we supply this input. Okay, the output of this operation, the convolutional operation, is applied to an activation layer. So what is an activation layer? So in this case, there are various types of activation layers. In this case, this network has a ReLU activation. So this one takes the input of the output of the previous layer, and then performs an operation. In this case, this is actually what happens. So it takes and slides over the image, the input. So in this is a 62 by 62 feature map, and then it takes a maximum. Okay, if it takes a pixel and then compares it against 0, so that's the ReLU activation layer operation, and then it takes a maximum between these two, so the pixel value and 0, and then selects the maximum. So it does all this, and then you see after this we find another feature. So this is the output of this activation layer. You can notice the impact this layer has on the activation map of previous neurons throughout the layer. So after this, now the output of this activation layer is applied to another layer. So various networks has various number of layers, and in this case we have just a few layers. There are three convolutional networks and a few activation and then other. So in this layer, the same happens for this convolutional layer. We also still apply a convolution against a kernel map. We apply a bias and then get an output. So this again is also applied to another activation layer, which we already discussed. So, and then from this activation layer, there's another type of layer which is called max pooling. So in this case, we are trying to reduce the dimension of the features. And then, for example, this already is a 60 by 60 layer. So we apply a max. A max, we take a size of a kernel. In this case, we have 2 by 2. So we consider we swipe through this feature map, and then for every 4 pixels, we extract the maximum. So at the end of this operation, we'll have a reduced size. So in this case, we have actually reduced the input feature map to a 30 by 30. So that's actually by half. So that's actually what the max pooling does. In other cases, we may use an average pooling where we take an average of 4 pixels and then output the average. There's the maximum, there's the minimum. So in this case, we are using the max pooling layer. Okay, so after this, we again supply this input to another convolution layer. Of course, these layers, as I explained earlier, they are to extract more features, to distinguish between input images, so that at the end of this, we are able to classify an image to a certain class. So here it takes all these images and then takes them through another convolutional layer, neural network, and then the same operation, just different kernels, of course, different weights, and the target is here is to extract the different features. So in this convolutional layer, always and mostly after any convolutional layer, there's an activation layer, and of course in this case we're using the rectifier linear unit, the ReLU. And then after this, of course, this is the ReLU operation. As I explained, we are getting the same size of the image. See now at this point we have reduced the image to 28 by 28 pixels. And then the same convolution happens, another convolutional layer, another activation layer, and another max pooling layer. So this is where we are. We are almost close to the end of the network. So something happens at the end of the network. So when we want to classify, so what happens? The outputs of a max pooling layer, they are actually flattened. So all these images, if we have a layer, in this case is 13 by 13 by 10, so it becomes a flattened layer. So we arrange all the pixels into one single line. So this is the flattened layer. So this is the flattened layer. So all the pixels in this layer, the max pooling layer, they are flattened into this dimension. It's a one-dimensional layer now, and all these are put together, put in one layer dimension, like an array, a very long array. And then, so what do we do with this? So we want to classify the image using this flattened layer. So here comes some. So what you do for every image, you sum all these values and then add a bias that was learned during the training, and then apply it to a softmax function. So what is a softmax function in this case? A softmax function actually serves a very a key purpose is to make sure that the CNN outputs a sum that is up to 1. So we are actually trying to obtain a probability for every of these, a probability to every of these possible outputs. So if we had input a certain image, we want to classify it based on a probability that it's in a certain class. So because at this end, we want to classify the image. So the softmax function is to normalize the logits. Of course, the logits in this case are the various summations of all the flattened layers or pixels. So we have a lifeboat. We want to find the probability that the input image is a lifeboat, that the input image is a ladybug. So the output sum should be 1. So of course, so we want to use the softmax function to obtain the probability that this input is in a certain class. So these are very important place to understand how really the CNNs actually classify images to a particular class. So a softmax function is actually its expression is that you take an exponential of all the of a particular uh, class. So for example, we sum all this flattened layer of this class. For example, this is the lifeboat. We do an exponential of this, divide by the exponentials of all these other classes. Of course, we have 10 classes. So a summation of all the exponentials of the various summations, we divide, we get a certain. So for this case, for example, the lifeboat has a 0 probability. So it means the image that was input is very far from being a lifeboat. Then, for example, we have a ladybug. Probability that the input is a ladybug is 0.003. So that also means that it's very unlikely to be a ladybug. So for example, the espresso here in this case has the highest probability, 0.88. So it means the input image, and of course it's highlighted here, is an espresso. So an espresso, I mean, it's the highest probability, and this is actually the classification of this image. So if, for example, change the input here to a school bus, so all these convolutions will change. It does the calculations, and then you'll see at the school bus probability is now 0.99. So this is how we actually check that we find the classification of these logits of the input. So at the end of it, we obtain probabilities. So we give it an input image, it does the convolutions, the activations, and then various other operations like the pooling so as to reduce the size and the dimensions of the features. At the end of the neuron, we have an flattening layer where we expand or flatten various input features, and then do a softmax operation to give us a probability so that this image is in a certain class. So at the end of this, we obtain probabilities. Now, once you get these probabilities, you can now tell based on the probability that this image is in this class. So for this case, we have the school bus, we have a probability that is 0.99. So it's unlikely that you will get a 1, but if you sum all these values, of course, by loss probability, we should have 1. So this is a school bus. So again, for example, if we take this image here, so again, what it happens in a simple, this is a ladybug. So we have the three channels. We extract the various features. As you can see, the visualization is very nice. You can see actually what we are trying to do. We are trying to obtain features from this image. So various images, and remember the kernel concept, where we apply a kernel of trained weights and then we sum all this and then supply to the next layer. So at the end of this, we are able to classify that this image is a ladybug. So using the softmax uh, classifier function. Of course, when you study these neural networks, there are other classifiers, but this most common one in this case is the softmax function. And then we have our probabilities. So actually, I find this tool very important to give you like a visual explanation of how a convolutional neural network works. And for me, it really helped me to visualize this concept earlier on when I started working on deep learning and convolutional neural networks. So you can actually go to the website. It's developed by some guys using TensorFlow uh, plugin of the web browser. It's using JavaScript. So you can actually interact with it. You can add an image and see its classification. Very nice to help you understand and visualize the convolutional neural networks. And then yeah, I hope this helps you to have a clear vision and visualization of these neural networks. Okay, thank you.